Hello everyone and welcome to another SI video. I'm Amanda and today we are going to go over AVL trees. To do that, we will go over what it means for a tree to be balanced, how to insert and delete a node to a tree, and how to rebalance an AVL tree. AVL trees are just like binary search trees, but balanced. So what does that mean? An unbalanced tree will always fall under four basic cases. Either a long strip going to the left or going to the right, resembling a linked list, or zigzag in either direction. These patterns are fairly easy to recognize visually, but how do we check for imbalance in our code? The answer to that is a property we call balance factor. Now, the balance factor of a node is the difference between the height of its left subtree and its right subtree. And the height is determined by the number of edges coming down from the root, with the exception of null children, which have a height of -1. So for instance, if we were to calculate the balance factor of the root, we would first go to the left subtree starting at 2. We see that its height is 2. We look at the right subtree starting at 7. Its height is also 2. And we take the difference between that and we get a height of 0. For 7, its left subtree has a height of 0. Its right subtree has a height of 1. And we take the difference of those two and we get -1. An AVL tree is considered balanced as long as each of its nodes never exceed a balance factor of above 1 or below -1. If we look back at our AVL tree cheat sheet, we can see that there are balance factors for the root of the tree and its child corresponding to each imbalance case that we have to deal with. Now with that in mind, let's go look at insertion. Here we have the code for a binary search tree insert and an AVL tree insert. And if we compare these two code snippets, we can see that they're pretty much exactly the same, all except for this little bottom portion that basically checks whether the tree is balanced or not. We first look at the parent of the node we just inserted. Then we call our rebalance function and continue that process up to its parent until we either hit the root or an imbalanced node. The same applies for deletion. It's not as clear in this example, but if you look really closely, you'll realize that this is the exact same algorithm, excluding, again, this one extra step here we have at the bottom. So now let's actually take a look at that rebalance function. The process is pretty simple. First, you update the height of the current node. You get the balance factor of that node, then its children, and then rotate as needed. Again, refer to this cheat sheet in your book to figure out what you need to do. I highly recommend to especially pay attention to how these subtrees move around when these nodes rotate. So if you ever get lost, refer to this, or even better, try to look up a tree visualization website online, and I'll include one in the description below for you to look at as well. So now let's go over a couple of examples. First, let's insert 15 into the tree. To do that, we traverse down the tree and insert just like we would in a binary search tree. Then, starting from 16, we check the balance factor and work our way up until we either hit an imbalanced node or the root. As you can see, 9 is imbalanced with a balance factor of -2, and its child has a balance factor of 1, which means that we have the right-left case. And so what we do is we first rotate right, which gives us the right case. And then to fix that, we just simply rotate left. Now if we check our balance factors from 15, we can see that our tree is now balanced. Now let's try deleting 5 from the tree. Since 5 is an internal node, we look for a successor, just like with a binary search tree. Then we swap the values and delete the leaf node, like so. And now we can start checking for imbalance starting at 7. Immediately, we find that 7 is in balance with a balance factor of -2, and since the child has a balance factor of 0, we're dealing with the right case. Now, it might seem odd since if we look at our cheat sheet, it never mentions a case where the child's balance factor is 0. However, if we look at our code, we can see that the only thing that matters is if we have a balance factor of -2 and 1, and 2, and then -1. So essentially, we're just checking if the signs are opposite. Now, going back to our example, since we're dealing with the right case, we simply just rotate left, and then we have our balanced tree. If we can check our work, it is indeed balanced, and we are finished. And that's all the time we have for today. So thank you for watching. And again, if you ever need help visualizing rotations for AVL trees, check out the website I put in the description below. And I will see you guys next time. This is Amanda, signing off.